All right, so moving on to Chapter 2 now. Chapter 2 is all about right triangle trigonometry. And so we're going to kind of take a step back and redefine the trig functions in terms of right triangles now. So it just helps to have a few different perspectives, I guess, to really solidify our understanding of the trig functions. So here's how we define the trig function values for acute angles. So by acute, of course, we mean the angle is less than 90 degrees, right? It's between 0 and 90 degrees. So if A is an acute angle, then sine A is, well, it's the same definition that we gave before. Sine A is y over r. But in the context of a right triangle, it would be the side opposite of the angle A divided by the hypotenuse of the right triangle. So it's opposite over hypotenuse. Cosine A is going to be the side adjacent to A divided by the hypotenuse. And then tangent A is going to be opposite over adjacent. Okay? So the way that I remember this is I use a little acronym called Socatoa, right? Which you may have heard of before. Socatoa. But Socatoa is how I remember, right? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Socatoa. So I'll give you an example of Socatoa in action so that you understand kind of these definitions. So let's find the sine, cosine, and tangent values. That should be an N, not an H. The sine, cosine, and tangent values for angles A and B in this triangle. So let's say we have this right triangle, ABC, and let's say that this side is 13, this side is 12, and this side is 5. Obviously, the figure is not drawn to scale. But give the video a pause and see if you can find the sine, cosine, and tangent values for angles A and B. Okay, so here's my solution, right? So as far as sine A is concerned, I know that sine A is opposite over hypotenuse, right? Opposite. So the side opposite of A is the side that's, you know, that A kind of opens up to. So it's 5 over 13. So there's sine A. Cosine A is adjacent over hypotenuse. That's going to be 12 over 13. And tangent A is opposite over adjacent. That's 5 over 12. Now we can do the same thing for angle B, right? Sine B is opposite over hypotenuse. That's 12 over 13. Cosine B is adjacent over hypotenuse. That's 5 over 13. And tangent B is opposite over adjacent. So that's 12 over 5. Okay, so that's that. One thing that you may notice looking at this example is that sine B is the same as cosine A, and sine A is the same thing as cosine B. And that's because of the cofunction identities that we're going to discuss here in a second. But first, let's just say that that's going to be true in general, right? So if triangle ABC is a right triangle where C is your 90-degree angle, then sine A equals cosine B. And here's the proof of that, right? So if you've got a right triangle ABC, the way that we label the sides of a triangle is that we label the side opposite of the angle with the same letter in lowercase. So if this is angle A, then this is side A. If this is angle B, then this is side B. And if this is angle C, then this is side C. Okay? Now, if you think about what is sine A, sine A is opposite over hypotenuse. That's A over C. And on the other hand, if you think what's cosine B is adjacent over hypotenuse. That's still A over C. So sine A is the same as cosine B. Okay. Another thing to note is that if triangle ABC is a right triangle, then A plus B has to equal 90 degrees, right? Because the sum of the angles of the triangle have to be 180, but 90 degrees is already taken care of in angle C, right? Angle C is a 90-degree angle. So that means A and B have to make up the other 90 degrees, right? So A plus B has to equal 90 degrees. And if you solve for B, then you get B equals 90 degrees minus A. So another way to say that sine A equals cosine B is to say, well, B is the same as 90 degrees minus A. So another way to say this is to say that sine A equals cosine of 90 degrees minus A, right? So sine A equals cosine of 90 degrees minus A. And similar statements are true for the other trig functions. So those are called the cofunction identities. Okay, so for any acute angle A, right, sine A is cosine of 90 degrees minus A. And similarly, cosine A is sine of 90 degrees minus A. And then you have the same thing for the other cofunctions. So sine and cosine are cofunctions. Secant and cosecant are cofunctions. Tangent and cotangent are cofunctions. Okay? So these are not the same pairs as the reciprocals, right? Remember, the reciprocal of sine is cosecant. The reciprocal of cosine is secant. Okay? The only functions that are both reciprocals and cofunctions are the tangent and cotangent functions. So they're kind of nice in that way, I guess. But anyway, those are the cofunction identities. Let's practice using them. So let's write each function in terms of its cofunction. Okay, so I'll give you an example of this so that you understand what it is that I mean. So looking at tangent of 63 degrees, the cofunction for tangent is cotangent, right? So if I want to write this in terms of its cofunction, I would say, well, this is equal to cotangent of something, right? It's equal to cotangent of 90 degrees minus 63 degrees. What is 90 minus 63? 90 minus 60 is 30, so 90 minus 63 should be 27, I think. So this is cotangent of 27 degrees. Okay? So here are a couple more. Go ahead and give the video a pause and try these out. See if you can rewrite cosine of 21 degrees in terms of its cofunction, and then see if you can do cosecant of 17 degrees in terms of its cofunction. Okay, so let's see. Cosine 21 degrees, that should be sine, right? The cofunction for cosine is sine. So this should be sine of 90 minus 21. So what is that? 69, I think? So this is sine of 69 degrees. Cosecant 17 should be secant of 90 minus 17. And that's 73. So this is secant 73 degrees. Okay, so that's how cofunctions work. Here's another example of using cofunction identities. So let's find one solution for this equation, secant 2 theta minus 7 degrees equals cosecant theta plus 25 degrees. Okay, so what I'm going to do is I'm going to rewrite one of these in terms of its cofunction, right? Because notice that secant and cosecant are cofunctions of one another. So I can rewrite one of these things in terms of the other. It doesn't matter which one you pick. I think I'm going to change cosecant into a secant. So I'm going to say secant of 2 theta minus 7 degrees equals secant of 90 degrees minus theta plus 25. Okay, right? So I changed the cosecant to a secant, and then I'm doing 90 degrees minus that angle. So in other words, I've got secant of 2 theta minus 7 equals secant of negative theta 90 minus 25 should be 65. So plus 65 degrees. Right? Well, if there are infinitely many solutions to this equation, but we're only asked to find one of them. And probably the easiest one to figure out is to say, well, if secant of this thing equals secant of this other thing, one way that can happen is if the two things equal each other, right? So I can just drop the secants and say, well, this is one solution, right? One solution is going to take place whenever the arguments are equal. And then you just solve for theta. So I can add theta to the other side, and then add 7 to the other side, and then divide by 3. Oh, isn't that lucky, right? 72 is 9 times 8, so I can divide by 3 and get 3 times 8, so that should be 24. So theta's 24. There you go. There's one solution. Right? There's one solution. And it requires us to use a cofunction identity to find it. Okay? So a couple examples of using the cofunction identities. Here's another fact that I want to talk about. So let's say that A is an acute angle, right? As A increases from 0 degrees to 90 degrees, sine A is going to increase, cosine A is going to decrease. So we'll look at both of those, and then we'll also look at the other 4 cases, right? So tangent A is going to increase. That'll be a little bit easier to see in a second when I show you a graphic. Notice that since cosecant is the reciprocal of sine, if sine is increasing, then cosecant is decreasing, right? So in other words, cosecant is 1 over sine. If sine gets really, really big, 1 over sine gets really, really small, right? So cosecant is going to decrease. In a similar way, if cosine is decreasing, then secant is going to increase. And if tangent is increasing, then cotangent is going to decrease because of the reciprocal identities. So what I want to do is I want to show you this thing in Desmos that I'm referring to down there. So here we have a circle. And I'm going to let theta, or in this case I think I'm calling it A, but I'm going to let A increase from 0 to 90 degrees. And as it does that, we'll talk about we'll talk about what's happening, what's going on, right? So remember that. Well, actually, you don't really know this yet. So let me explain. This circle is the circle x squared plus y squared equals 1. It turns out, and we'll talk about this in more detail in the future, but it turns out that when you have this circle is called the unit circle. When you have the unit circle, the x-coordinate of any point on the unit circle is cosine of the corresponding angle, right? And the y-coordinate is the sine value. So, and that makes sense, right? If we're talking about the unit circle, then the radius of any triangle, so let me just get a triangle going here. So you've got this right triangle. The radius, or the hypotenuse of the triangle is the same as the radius of the circle. The radius of this circle is obviously 1, right? So that means that if you're looking at sine of this angle right here, it's going to be y over 1, which is just y. And if you're looking at cosine of this angle right here, it's going to be x over 1, which is just x. So cosine is x, and sine is y. So if you imagine that theta is increasing, what's going to happen to y? Or in other words, what's going to happen to sine theta? It's going to increase, right? Notice that y is getting bigger and bigger and bigger as x gets bigger and bigger. So that tells us that sine theta increases as theta increases. Meanwhile, what's happening to cosine? What's happening to cosine theta? Cosine theta is x. Notice that as theta increases, x decreases. Right? So cosine is getting smaller and smaller and smaller the larger that theta gets. So you can see that as theta increases from 0 to 90 degrees, sine theta increases as well, but cosine theta decreases. So now, if you think about tangent, what's going to happen to tangent, right? Well, tangent is sine over cosine. Tangent is sine over cosine. So if tangent, so if sine is increasing and cosine is decreasing, then tangent's going to increase, right? It's like, imagine that tangent, maybe you're starting at like 5/10, right? But then sine increases, maybe, so it goes up to 10 or something. I mean, this isn't quite right because sine lives between -1 and 1, right? But I'm talking about the ratios here. So if you're starting at 5/10, that's the same as 1/2. But then if sine increases to 10 and cosine decreases to 5, then tangent would be 10 over 5, which would be 2. So if sine is increasing and cosine is decreasing, then tangent's also going to be increasing. The other three just come from the fact that they're reciprocals of the first three, right? So anyway, these are useful facts to have memorized, right? As theta increases, sine increases. As theta increases, cosine decreases. So as theta increases, sine increases, cosine decreases, tangent increases, right? So those are all important things to know. Let me give you an example of working with this. So let's fill in the blank with the correct inequality, less than or greater than. Okay? So let's say that we're comparing cosine of 65 degrees to cosine of 35 degrees. Now the question is, should we put a less than or a greater than in that spot? Well, we know that as theta increases, cosine decreases, right? So that conversely, we could say as theta decreases, cosine increases, right? So as theta decreases from 65 degrees down to 35 degrees, cosine theta is going to increase. That means that cosine of 35 degrees is actually bigger than cosine of 65 degrees. So cosine 35 is bigger than 65, or in other words, cosine 65 is less than cosine 35, right? So we should have a less than sign there. I'm going to just put a few more of these on the page and let you work them out. Feel free to give the video a pause and fill in the blanks with the correct inequality. Okay, so see if you can fill in those blanks correctly. Okay, here are my solutions. I think we should have a greater than here because tangent decreases as theta decreases. For secant increases as theta increases, so I'm thinking the inequality should be going that way. Cosecant decreases though, so I think the inequality should go that way, right? Cosecant decreases as theta increases, so cosine 15 should be more than cosine of 75. Let me give you another example of this though. So we can mix and match because we have the cofunction identities, right? So we could compare something like sine of 15 degrees to cosine of 80 degrees. And the way that we would do that is first we would rewrite one of these in terms of its cofunction. It doesn't matter which one. I think I'm going to change cosine and rewrite it in terms of sine. So I have sine of 15 degrees. Cosine of 80 degrees would really be the same thing as sine of 90 degrees minus 80 degrees. So that's 10 degrees, right? So sine increases as theta increases. That means sine of 15 degrees should be bigger than sine of 10 degrees, right? So that's how you would do that. So to answer the first question, you would say sine 15 should be greater than cosine of 80, right? So you can also kind of mix and match with stuff. Okay. The last thing that I want to talk about in this section is that I'm going to have you memorize the trig function values for certain angles. And the way that I'm going to prove to you that these are the trig function values is by looking at a couple of special triangles. So the first kind of special triangle that I want to show you is the 30, 60, 90 triangle. And to form the 30, 60, 90 triangle, I'm actually going to start by looking at an equilateral triangle. So if we give ourselves an equilateral triangle, we know that all three sides are the same length. Okay? It doesn't matter what we call that length, but to make the math easier to work out, I'm going to call each of these length 2. The other thing that we briefly talked about with equilateral triangles is that if all of the sides are the same, then the angles also have to be the same. And since the angles of a triangle have to add up to be 180 degrees, that means that the angles of an equilateral triangle must all be 60 degrees, right? Because 60 times 3 is 180. Okay? Now, I make a 30, 60, 90 triangle out of this by dropping a perpendicular line from here down to its opposite side. So that's perpendicular now. If I do that, then I've bisected this angle so that this is 30 degrees now. This is 30 degrees. And I've also bisected this side so that this is now length 1 and length 1. That's why I wanted to start with length 2, right? So that when I divide it, it comes out as a nice whole number. But if we kind of split this up now, I'm just gonna look at one of these triangles. I'm gonna look at this triangle right here. Okay, so redrawing it. Here's what I've got. Well, this is fine. Okay, so I've got a 30-degree angle up here, a 60-degree angle down there, and then this is a 90-degree angle. I know that this length is 1, and I know that this length is 2. Okay. Now I can solve for the missing side by using Pythagorean theorem, right? So I can say x squared plus y squared equals r squared. So in other words, 1 squared plus y squared equals 2 squared. So y squared is 4 minus 1, that's 3. Okay. Now, since theta is acute, I know that I'm going to be in quadrant 1, right? So when we're dealing with right triangle trig, the angles that we're dealing with are always acute. And so thinking back in terms of like chapter 1 stuff, we would be dealing in quadrant 1. So when I take the square root here, since I'm in quadrant 1, y is going to be a positive value. So it's going to be y is positive square root of 3. Okay. Now, based on that triangle, we can come up with the trig function values for a whole bunch of stuff, right? So we know, for example, that sine of 60 degrees is going to be opposite over hypotenuse. That's root 3 over 2. We know that cosine of 60 degrees is going to be adjacent over hypotenuse. That's 1/2. And we know that tangent of 60 degrees is going to be opposite over adjacent. That's root 3 over 1, which of course is just root 3. Okay, and so forth for the other 3 trig functions. We can also get values for 30 degrees. And by the way, I guess maybe I should say this, right? So this is true regardless of the number that you start with here. So if instead of choosing 2, I had chosen something else like maybe 6, then when I bisect, these would be 3. And so here I would have 6 and 3. And when I go to do the Pythagorean theorem, I would have x squared plus y squared equals r squared. I would get 36 minus 9. 36 minus 9 is 27. And then the square root of 27 would be 3 times the square root of 3. Okay? So when I went to go do, sine of 60 degrees, so I'll do it up here because I don't want to mess up what I have down here. So, but when I went to find sine of 60 degrees, it would have been, so this would have been 3 root 3, right? So sine of 60 degrees would have been 3 root 3 opposite over hypotenuse, 6. But notice that you can reduce, right? You can reduce and you get root 3 over 2, just like we got before, right? Just like we got before. So it doesn't matter what number you start with. I started with 2 because it makes the math easier, because you don't end up having to do any reducing if you start with 2. But any number will work. So what that tells me is that sine of 60 degrees is going to be root 3 over 2, regardless of how big the triangle is, right? It doesn't matter how big the triangle is. Sine of 60 degrees is always going to be root 3 over 2. Cosine of 60 degrees is always going to be 1/2. Tangent of 60 degrees is always going to be root 3. And we can get similar values for 30 degrees, right? We can say sine of 30 degrees is always going to be, I'm going to use the crossed out values so that I don't have to reduce later, but sine of 30 degrees is going to be opposite over hypotenuse, that's 1/2. Cosine 30 degrees is going to be adjacent over hypotenuse, that's going to be root 3 over 2. And tangent to 30 degrees is going to be opposite over adjacent, that's 1 over root 3, which if you rationalize that, you get root 3 over 3. And similarly for the other 3 trig functions. Okay? So we can memorize these values for 60 degrees and 30 degrees. We can memorize what the trig function values are. Okay? The other special right triangle that I want to show you is the 45, 45, 90 triangle. So 45, 45, 90 triangle would look something like this. So a 90 degree, and then a 45 degree, and a 45 degree. And if we know that both of those angles are the same, then that means we know that both of these sides are the same length. So really, we've got an isosceles triangle on our hands, an isosceles right triangle on our hands. So we can call these side lengths whatever we want. I'm going to call them both 1 to make the math a little bit easier to work out. But again, you could call them anything you like. And then I can use Pythagorean theorem to solve for the hypotenuse. So I can say x squared plus y squared equals r squared. 1 squared plus 1 squared is r squared. So r squared is 2, and that means r is the square root of 2. And so what does that tell us? Well, that tells us that sine of 45 degrees, sine of 45 is going to be opposite over hypotenuse. That's 1 over root 2, or in other words, root 2 over 2. Okay, cosine 45 degrees is going to be adjacent over hypotenuse. That's 1 over root 2 again, root 2 over 2. Tangent of 45 degrees is going to be opposite over adjacent. That's 1 over 1, which is just 1. And so forth for the other 3 trig functions. Okay? And again, that's going to be true regardless of how big the triangle is. Like I said, you could replace this with some other value. But what that tells us is that sine 45 degrees is always root 2 over 2. Cosine 45 degrees is always root 2 over 2. And tangent of 45 degrees is always 1, regardless of the actual triangle you're looking at. Okay. So we can summarize this as follows. So we're going to summarize it in a table. So let's complete the table below. And I'm going to tell you, you should memorize these, right? So note, you should memorize. You should memorize these. Trig is kind of a strange math class in the sense that, contrary to popular belief, math is not about memorizing a bunch of stuff. Math is not about memorizing a bunch of steps to take to solve problems. Math is about understanding, right? Math is about logically understanding how to do something. If you understand the logic behind something, then there's a lot less memorization that you have to do compared to a class like, anatomy or something, where basically you're just memorizing information, right? In math, you're really not memorizing so much. You have to memorize some things, but you're mostly just applying that information. Trig is a little bit different. There's a little bit more emphasis on memorization in Trig, that's for sure. And so you should try to memorize these values. Of course, in an online environment, there's no way for me to know whether or not you've memorized the values, but just trust me that it's going to make calculus a lot easier if you have these values memorized, okay? So try to memorize the following values. But here's the table. So let's do this. Let's find the 6 trig function values for each of the following angles. So let's do sine theta, cosine theta, tangent theta, and then we'll do their reciprocals as well. So cosecant, secant, and cotangent. Okay, and the angles that we should have memorized are 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. Okay. So I'm going to let you go ahead and pause the video and see if you can fill this out on your own from memory. See if you can do it from memory. It would be a good exercise for you. Okay. So now here are my solutions. Sine of 0 degrees is 0. Cosine of 0 degrees is 1. Tangent is sine over cosine, so this should be 0. Cosecant is 1 over sine. 1 over 0 would be undefined. Secant is 1 over cosine. And cotangent is 1 over tangent, or it's cosine over sine, however you prefer to think about it. But either way, that's going to be undefined, right? Division by 0 is undefined. Now 30 degrees. Sine of 30 degrees. Sine goes with your y values, okay? So sine of 30 degrees is going to be 1/2. Sine, I'm just going to fill out sine. Sine of 45 degrees is going to be root 2 over 2. And sine of 60 degrees is going to be root 3 over 2. The reason I wanted to do that is just to show you. Remember, sine goes with your y values, and sine increases as theta increases. So you can think of 1 as like the square root of 1, right? So notice that we're increasing root 1 to root 2 to root 3 as theta increases. So you just need to memorize 1/2 root 2 over 2 and root 3 over 2, and then know that for sine those values increase. For cosine it's the exact same values but in the opposite order because cosine decreases as theta increases. So for cosine we're going to start at root 3 over 2 and then work our way down to root 1 over 2. Whoop, don't need the square root down there. So let me rewrite it. 1/2. Okay? And here you just would have 1/2. Anyway, sine of 90 degrees is 1, cosine of 90 degrees is 0. And based on that, you can fill out everything else, right? Because you know that tangent is just sine over cosine. So 1/2 divided by root 3 over 2 would be 1 over root 3, which if you rationalize it is root 3 over 3. Root 2 over 2 divided by root 2 over 2 is just 1. Root 3 over 2 divided by 1/2 is just going to be root 3. And then 1 divided by 0 is undefined. Right? So there's tangent. Cotangent is the opposite, right? It's cosine over sine. So it's going to be root 3 over 2 divided by 1/2 is root 3. Root 2 over 2 divided by root 2 over 2 is 1. And then 1/2 divided by root 3 over 2 is 1 over root 3, which is the same thing as root 3 over 3, depending on if you want to rationalize it or not. And then finally, 0 divided by 1 is just 0. So those are the values for cosecant. Oh, shoot. No, I just did cotangent, didn't I? So I'm going to cheat. I'm going to change this to cotangent. So I did cotangent, and then I'll make this one cosecant over here. Got ahead of myself. I apologize. These are the values for cotangent. Anyway, let's do secant and cosecant. Secant is 1 over cosine, right? 1 over 1 is 1. 1 over root 3 over 2, that's just 2 over root 3. Or in other words, 2 root 3 over 3, if you rationalize it. 1 over root 2 over 2 is 2 over root 2. So in other words, that's 2 root 2 2 over root 2. If you rationalize, you get 2 root 2 over 2. That's just going to be root 2 if you rationalize it. 1 over 1/2 is just 2. 1 over 0 is undefined. And then for cosecant, cosecant is 1 over sine, right? 1 over 0 is undefined. 1 over 1/2 is 2. 1 over root 2 over 2 is 2 over root 2, which is the same thing as root 2. 1 over 3/2 is 1 over root 3 over 2 is 2 over root 3, which if you rationalize, that's 2 root 3 over 3. And then 1 over 1 is 1. So there you go. So those are the values for the trig functions. What it boils down to is memorizing sine and cosine. If you can memorize sine and cosine, then you can fill in the rest of the chart pretty easily, just by knowing quotient and reciprocal identities. So that's that. That's all I have to say for this section. We will see you in the next one. Whoops.